Hi everyone, welcome to the last session before the keynote session on AI and autonomous systems. Our first speaker in this session is Professor Sarit Kraus. Sarit is a professor of computer science at Bar-Ilan University. She is highly recognized for her contribution to the area of multi-agent systems and strategic negotiation, interface of artificial intelligence and game theory. She's an ACM and AAAI fellow, and she received many prizes, including Ichkai Prize. And interesting prize is the one she received from, or an award from the city of Los Angeles for her contribution to randomize, again, the power of randomization, randomized security policies that are actually being used at LA International Airport. Thank you, Sarit.
And thank you for inviting me. And I would like to talk about robot, human collaboration, and learning for improving human well-being. So people are getting old. In the sense, the community, the number of people that are old in the community are increasing. And while this is maybe good news, there is also a problem. And the problem is that it's extremely difficult to take care of all the people that has these needs. And I'm taking my research personally, so we have some difficulties with my mother that needed help, and we ran into a lot of troubles. And I was wondering, why won't we have a robot at home that will help us? And the reason is that while there are today robots that can do all sorts of activities, there are robots that can fold laundry, there are robots that can make coffee, there are robots that can even pick up a person and maybe wash it, they are still not in the state that we can buy such robot and deploy them at home. And there's a problem with using robots in important situation and domains is not just in the homes. I thought, okay, the home is some complex setting, unstructured, and everybody is different. Okay, so I understand why we still don't have robots at home. But even in agriculture, there are a lot of effort to automate and incorporate autonomous machines into agriculture, but I have also friends in AI and agriculture, and there still need people to be involved. Even in such relatively structured environment, there still need for people to be involved in running all these autonomous machines. Now, if we're going back to the home robots, so I would like to distinguish between two types of robots. So they are companionships robots. They are the ones that are talking to you, reminding you to take your medicine. There are quite a lot of progress in these ones, but I'm not interested in this kind of robots. I prefer that people will talk to people, but I'm talking about functionality robots. Robots that do actions in the house. And in this, we are really not ready to deploy robots. Why? So one issue is that there are technology problems in the hardware, in the perception and the actions when robots are acting in unstructured environment and highly variable environments. Okay, so this is not something I can contribute because I'm not a hardware person. But on the other hand, one of the problems with robots in the home is that there are many tasks, and the tasks varied, and they are changing, and one person needs that, and another person needs that, and the variety of tasks make it very, very difficult. And another thing is that while there are robots, especially in industry, that are specialized to do something, that's we know how to do these days. In home, and even in agriculture, what we really need is general purpose robots. And you know, even software, we rarely have some general purpose software that does many things. You know, there are robots that play, there are softwares that play Go, when there are softwares that do databases, but general purpose software is really rare, and general purpose robots, it's almost impossible these days. So what I propose is to think of the options of teleoperating robots. And teleoperating robots can be done by the person itself, if he's in good shape, can be done by his family members, and can be done by operator. What do I mean by teleoperating the robots? Now, there is a robot at home. He has all sorts of capabilities, but he doesn't know he's autonomous. In some of the sense, he can go from point A to point B. Okay, but he has a camera. So a person, you know, if someone needs to feed the patient, or the user, I will call him, you know, it is really not difficult to teleoperate the robot and to feed the person, even to pick up the person and to put him in the bus, or to get him dressed. All these things can be done by somebody from far away, can teleoperate the robot. Now, think about it, that most of the time, the robot is not needed. You know, we were thinking that we need, for my mother, we had one person at home, but it wasn't enough. We said we need two. As in Hebrew, you said, Ovdim Zarim. Yeah? But it's not that we need them all the time. And similarly, the robots is not needed all the time. So think about it. There are these people, operators, that sit in some center, and they can teleoperate the robots. Now, they can do time sharing. Why? Because it's not that one needs to operate the robot all the time. You know, one person wakes up at this time, and then somebody needs to help him sit up. Okay, and then another time, etc. So we can think about the idea that robots will be at home, there will be a center of people sitting somewhere and teleoperating many robots simultaneousing. Now, this is how it will work. They have some interface. They see what the robots seeing in some, and you can do virtual reality. There are many ways to teleoperate robots. And actually, there was a project, EU project, where they tried to see if it is possible. And they came up with the result, yes, it is possible. So I was thinking, okay, why it is not deployed anywhere? So it turns out that it is beginning. For example, there is a Japanese company called Mira Robotics that they give you services for laundry. So you buy this robot, it is at home, and it's not autonomous, but there are operators sitting in some places, and they teleoperate these robots. Some of, they are semi-autonomous. And they are doing your laundry, folding it, and all the process. So this is one example of teleoperating. There is another example having to do with trucks. So there is trucks that are driverless, autonomous trucks, that are in some place in Sweden. It's working in a mine, bringing stuff, and they are driving quite relatively slowly. But nevertheless, there is a team of operators. Usually one operator is enough because they are driving very slowly. And if there is some problem, the operator take over the truck from afar and does whatever is needed. So this is another example. So if we really want to push this approach of combining the knowledge of people with the abilities of robots. The question is, what is needed and what research question need to be answered in order to push this kind of deployments of robot further. So again, one thing that I'm not getting into it is that you'll have these robots that are you able to do all this action, especially if you teleoperate them. They are now quite expensive, but that's because they are building 5 a year. But I assume once it will get into practice and there will be many possibility to use it, the price will go down. So I'm not getting into it. But there are two sides of the project here. One is to help the operators in their work. This is not an easy sitting somewhere and managing many robots in different locations is a challenging. So supporting the operators. On the other hand, there is another thing we would like to do. These are all operators operating the robots. We want to move forward. We want the robots to become more autonomous, to do more things by themselves without the help of the operator. And the next question is, okay, why won't we collect all the data of the operators teleoperating the robots and use it as a data that will be for learning of the robots to improve their capabilities and become more autonomous, to do more things. So these are the two tasks, making agents that will support operators and learning from observation, from observing the operators working with the robots. So let me tell you about different research questions that came from this vision, and of course, there are still many open questions to handle. So the first task that looked quite reasonable was, okay, so these are all the tasks that are coming to the operators. We should allocate it to operators, and there are many constraints and problems to handle. Can we handle this task allocation efficiently? So, okay, what's the problem? This is an online task allocation problem. And unfortunately, it's quite difficult to optimize and find the bounds on the distance between the offline results and the online results. So then my student, Hanan, had some brilliant idea. He said, okay, let's look at the end of the day. After all the tasks arrived and they were handled, but forget how we did the online allocation. Why won't we look just at the task and the operators that were available at this given time? And let's look at all of them and solve the problems offline. Okay, this is still NP-hard problem, but nevertheless, let's do some near optimal solution. Now the question is, can we take this decision that the system did offline and use it to teach a classifier to compare between two assignments? Because when the system offline decided that this task will go to this operator, it also had considered this task to go to other operators and other tasks to go to that operator. So we have many pairs, and we know that the one that was chosen by the semi-optimized optimizer was the best. So now we can use these pairs to train a network, in his case, to compare between a task and operators that was allocated it. So this was the general idea. And since we don't have still now robots with operators, he was looking for a different complex task allocation and with a lot of data. And he looked at emergency room allocation. So in emergency room, there is online problem. There are all these people are coming to the emergency rooms, and there are all these doctors and nurses and stagiaires, and you need to allocate the people to the caregivers, I will say. Now he went to...
Emergency from left to right and ambulance from right to left. So you can see in the rear view mirror.
I don't know.
In the rear view mirror.
Anyway, he went to people in emergency room and asked them what are the things that they want to maximize. And there are many features, but he doesn't care. You know, he said, you give me the you give me the criteria, and I will try to provide you with a better system than what you do now. Do you know what their algorithm now? The algorithm now is, you know, if you are serious, everybody, you will be treated first, no question. But otherwise, it's mainly first come, first serve. And with some variations, they have some lines, different, but it's really... So, you know, this is a problem. People are coming, and you need to allocate them to people. So what he did, he first formalized the functions that they want to maximize, and given that, he created first a set of patients, and in our case, it took simulation of the Rambam Hospital. There are a lot of data about these emergency rooms, so he got data of patient flows. He's not interested how they allocated it, because it probably wasn't efficient, but he's interested what were the patients that came and who were the caregiver to give them support. Then he solved the problem offline. He used mixed integer linear program, and given the utility function, he solved it offline. It's not easy, but it's, the solvers now are quite good. And then he translates each of the assignment into learning data. And this is how, as I mentioned, this is a patient that was allocated to this caregiver, but he has other pairs. This patient are not allocated to this caregiver, or this patient allocated to this, not allocated to this, the same here. And now he knows that this pair was better than this one. Why? Because this was chosen by the global optimize. And etc. You know, patient is not a name, patient is a vector. I always say everything is vectors. In the worst case, they are matrices. Okay, and then he is training a model which needs to learn that if this one was, if X was chosen, so he was better than the Y, then he wants the outcome, what he tried to maximize is that O1 will be greater than O2. So this is the optimization problem. He has data, a lot of data, and he taught and he developed a training, and then he use it as online. He has a patient arrive. They are caregivers. He put them in the network. They are ranked, and then he used some majority rule to decide which patient to allocate, and so on and so forth. And as I said, he used simulations. There was a simulation of the emergency room in Rambam. Somebody did the simulation. There was a model of based on the real data. So he used this simulation from night and from day. And he shows that using this is what he improved. So this is a normal load. This is a heavy load. And you see this improvement according to the parameters that they ask us to look at, and it's quite nice that it is improved almost everything. Not the waiting time, by the way. Then we said, okay, does it depend on having a good optimizer for the offline problem? So we had another problem, which is assigning images like X-rays and other images to radiologists. So this is how the system look now. They get a list, they click, they get the picture, they give the reports. And of course, this is not efficient, given they have all sorts of parameters they need to maximize. The problem here is that we wasn't able to solve it using some mixed integers. So here we go. So we had to use Monte Carlo tree search to solve offline, but nevertheless, again, the result were, this was solved offline, and then using online, the same way was very efficient, led to very efficient. So this is an example of a project that came out of this vision that you have operators and they can teleoperate the robots, and we handle one problem of this problem. But the main problem, okay, this was just optimization, but the main problem is the people. And letting people manage this kind of task is quite difficult for the people. And the question is, can we develop agents that can support the operators? So we still don't have operators, as I said, but we had another project where there were many semi-autonomous robots that were moving around. And what they had to do, they had to look for green balls in my lab, okay? But never mind, the robots are quite cheap, and you can think of other tasks for the robots. And there is one person that is managing all these robots. So you may ask, why do you need a person in robots that are autonomous? They are doing everything by themselves. So there are three reasons, and these reasons also repeats in the teleoperating of the robots. One thing, in many cases, robots ran into some problems or they can't do anything, and the person take over and teleoperate them. Another thing is that some actions people do better than the software on the robots. For example, even though the robots can do it. These robots were looking around, they enter under my table, and it took them a long time to go out. On the other hand, the teleoperator just do, I mean, not me, I don't know how well to teleoperate these robots, but a good teleoperator, immediately take it out of his place. But the robot, they can do it, but it takes time. And the third thing is that in many situations, currently, people, the owners of the robots would like a person to make a decision and do the action. And this will also be in teleoperating the robot in homes, I still can think about actions that even if the robot will be able to do, you know, the owner, the robot would like a person to be involved. So these are these 10 robots in my lab moving around. Ariel Rosenfeld was a student. He's now a faculty member. The robots were moving around. People were overwhelmed. They can manage maybe 5 robots, but not 10. So what we did, we designed an agent that can help them. So in order to have this agent, we needed 2 models. We had a human model and the robot model. In the sense, how the activity of the human, how long it will take, and how will it help the robots in their activities. So we collected data on human behavior and on the robot's behavior in their task. And then we used the machine learning in order to build these models. And then, this was just the beginning, then there was optimization problem. What should the person do and in what order in order to increase the joint activity of the robot and the person. And then when he solves this optimization problem, he provides an advice to the person, to the operator. Now, saying collecting data. Okay, so collecting data on robot activity is not that difficult because you don't need a person around and you run, we had a very good simulation that actually mimics the world, but we could run it very quickly. So we collected 150 hours of simulations. Collecting data about humans' decision-making is much, much more difficult. And we brought 30 human operators into the lab. We ran it in simulation, not in real robots, because otherwise it would have taken much longer. Interestingly, the model that we collected with the simulation was quite helpful also in the real world. So in order to check whether this agent that gives advice to the operator is really helpful, again, we ran experiments with humans because this is unfortunate to us, because I don't know, computer scientists don't like to run experiments with people. I don't know if the people in biology and social science know about it. People are really annoying. They always ruin my experiments. But never mind. So we brought people to the lab, and in real robot and in simulations, they ran twice. Each of them came twice. Let me tell you about the real people. The question is how many green balls the robots can find when they have an agent helping the person and when there is no agent. And we brought 12 people twice, mixed ordered, one with the agent, one without the agent. And without the agent, on average, the robots, the agent wasn't for the robot, the agent was for the person, found on the 10 minutes experiments 7 balls. On the other hand, when there was an agent helping the person, they found on average 14 balls, which is amazing by itself, but more amazingly is that for all the 12 people, the robot found more green balls when there was an agent helping the person. So helping the person seems very helpful. And let me show you a video. One of the tradition of doing research with robot is a student making videos of the research. And actually, I thought, well, I'm not really a robotic person, and I didn't want the student to do I said, this is waste of your time. But then I said, no, we need to do a video. And they sent it to the competition of each guy video competition and won. And now I am using it every way. So now I say, okay, always listen to your students. Let's hope it will work.
Dispatch,
Quick! There's a student missing in the northern section of the campus.
give me the exact location. A unit is on its way.
In disaster environments, both the victims and the rescuers' lives may be in danger. Robot technology can provide solutions. Today's robots are semi-autonomous and require a human operator's help whenever they cannot handle the situation on their own.
Move Agent 3 away from Agent 4. Move Agent 4 away from Agent 5. Manually drive Robot 6 to a
The
better...
fast-paced, simultaneous streams of data from multiple robots can be overwhelming and can be a grueling task for a single operator.
Your robots are too close together. Spread them around. Your robots are too close together. Spread them around. Manually drive Robot 6 to a better position. Move Agent 3 away from Agent 4.
Here in Bar-Ilan University, we have developed an intelligent agent that supports the human multi-robot team collaboration. The agent prioritizes the different tasks, filters the robot's signals, and generates warnings which enhance the operator's situation awareness, thereby allowing him to make better decisions. The agent uses a novel methodology combining machine learning and optimization techniques, which accounts for both the operator's abilities and the robot's performance in real time. Through extensive empirical evaluations, we have shown that our agent was able to significantly enhance the team's performance, which can translate into saving lives.
There he is. We found him. We got him. I'm sending you the exact location now. Dispatch out.
Okay, but we ran more experiments in other situations like storage. Also, there are robots and there are a person that is packing and also teleoperating the robots when needed. So another research question that we have an ongoing project is how to help an operator that is not experienced by learning from observing experienced operators, and then using this data to advise less experienced operators. So I talked to you on the person side, and I'm saying, okay, we will learn from we will learn from the experienced people to help but can we improve the robot? Because this is eventually my goal. So the one thing that is common is using reinforcement learning for the robots to learn. And this is today the best way to teach robots to do something. So the question is, why won't we use the reinforcement learning to teach the robots to do all the tasks? This is a good way, and we are not making a lot of progress in this. Why? Because it requires a lot of exploration, and robots, even in simulation, collecting data takes a lot of time. And then there is safety issues with the robot and the reinforcement learning. Even think about a car. You don't want it to do reinforcement learning. So what could we do? So we suggested, I have a student, Elad Sarfian, that he is saying we can use non-expert observation, and in our case, it's a observation of the teleoperator to use it for improving the learning of the robots. Now, I want to emphasize that this data is not that good. Why it is not good? I want to compare between two types of learning. There is one learning from demonstration. Somebody wants to teach the robot how to do actions. So he demonstrates. He can do it by teleoperation. He can do it by actions that are logged, all sorts of things. But he will show the robot the best way to do the action. On the other hand, our data, which we called learning from observation, no one is doing it to teach the robot. What they are doing, they are teleoperating the robot because they had to do it. They need to feed the person. They are not thinking about how to teach the robot to do it. And sometimes they are not the best operators. But here is all this data that will be logged. And the question is, can we use it to improve their reinforcement learning? So the problem is to do it efficiently, and even if you learn from a demonstration, from observation, and to do it in a safe way. And in safe way, it means that the actions that are chosen by the robot in the reinforcement learning will not ruin the robot, will ruin the house, will hurt somebody. And even in simulation, it's very important to keep safety. So, I won't get into the details of the formal models, but you can imagine that reinforcement learning is built on top of Markov decision process. And the Markov decision process, the MDP, are not known to the robot because he doesn't know the environment. He doesn't know the environment, and he doesn't know the policy, the optimal policy. So so all the reinforcement learning is built on top of the Markov decision problem, and I won't get into the formal definition. Just think about it, that we have actually some trajectories of different people. Each of them has a different strategy that it uses. Maybe they don't have a real strategy, but at least, but we don't observe the strategy. We observe a trajectories of actions that were performed on the robot by the operators. So one possibility is to use an average-based strategy that look at, in a given state, what was the percentage of people that perform this action, and use this as a distribution over the actions that the robot will perform. Well, think about it. Some of the people didn't choose the best actions, and the question is, can we start with the average behavior policy and improve it? And that's what we did. For now, we did it on Atari game, which is the most studied game in reinforcement learning. And we wanted to show that we can start with the average behavior policy, approximate its value function, and then do stochastic improvement of the average policy, making sure the safety here, making sure that the action chosen will not lead to an average value that is lower than the average policy. So this is the safety criteria that we wanted to do. We ran 4 Atari games using data set of non-expert human players. In 2 out of 4 games, our agent achieves a compatible score for the reinforcement learning without running even one simulation, only based on the database of some non-experts that play this game. In 2 other games, it did better or comparable than the state-of-the-art policies. Yeah, you can see it also here, demonstrating both that we are here. These are the reroutes. This is ours, which is both better but also safe, because we want also to show that the average is higher than the other averages. So I'm almost finished. I would like just to say that now what we are starting to do is to move the reinforcement learning algorithms that we build from games like Atari, that is less challenging, into robots. The problem is that the policy of the robot are continuous, and the improvement state is not easy, and the quality of each human action policy is different. And in particular, there should be a lot of transfer learning between different actions and different settings, thinking about these operators that are teleoperating people in different settings, in different actions. And I think one of the most important idea will be a challenge is to do transfer learning, which I can give another talk in another opportunity. So this is one of our simulation. We are running robots and collecting data. You need to be aware of that even in simulation, running robots that are mimicking the real world is very time consuming. It's not just like running a simulation of games. So to summarize, I presented ways to move this vision of teleoperating robots in homes and maybe also in agriculture settings. You need to help the person, and you need to learn, so the robot develop algorithm for learning to make the robot more autonomous. And well, I hope when I will need these robots, the research will be end then. Thank you.
Very quick question. There is talk also about the possibility of teleoperating autonomous vehicles. What's your opinion?
So I gave an example. This is the trucks. That's what they are doing there. So it doesn't make sense that there will be a person that will teleoperate the car all the time.
Not on the highway, but in particular situations.
Yeah, so in some situation, I think there is still research that need to be done in order to support these people, to train them, but I think it's a solution, and that's why I gave this slide.
So you have agents that advise teleoperators. Why don't the agents advise the robots?
Okay, because they can also advise the robots in some sense, but we are still not feeling safe enough for advising the robots. So you still want the human to be involved because the quality of the advice, so here the advice is what to do first and things like that. It can give also, in the one for the inexperienced people, they give him an advice, but we are still not ready to run it on the robots because it's not safe enough. But, you need to make progress. And what I'm claiming, okay, we will collect data. And as we collect more data, we can use it for the learning. And meanwhile, we have service at home. So this is my idea.
Hi, follow-up to David's question. Was the teleoperating tried in the agriculture setting that you suggested that it is much more simpler?
So currently, they usually have somebody on the tractor, and he doesn't need to. It's like in autonomous cars that the person get involved just in I don't know of the concept of one operator managing many tractors. I'm just giving tractors as an example in different fields and saving time. And also you need to be an expert to do it. So it's better that it's in many fields and you don't want the the farmer not always know how to work with all these amazing but difficult to manage tools. So we are writing a proposal with somebody from agriculture and said that they are ready. This is probably more feasible than to do it than robots at home.
I have one more question, if no one else. Yeah, my mic doesn't work. So I read somewhere that in many systems now, actually the roles flipped. And for example, in Amazon, the people are packing and doing all the work, and the robots are supervising them. So I'm curious if we can do some teleoperating of robots to humans.
What I know that there are these robots in Amazon that bring the items to the packers, and they are packing, and there are also some automation there, and there are some team of people managing all these robots. And they have this center that they are looking around, but there are many people. And my question is, can we reduce the number of people? And can a robot also observe the person? Yeah, but why won't you let the robot do? I don't know why they are doing it, because probably they don't trust the robot yet.
Yes.
You don't trust the people yet.
You don't trust the people, exactly. I think that's the point. You trust the robots more than you trust the people.
No, but I'm asking, so why won't they let the robot do the packing if they...
Packing robot cannot yet do packing. Robots can move things around.
Yeah, that's what they are doing.
They supervise she's right, they're supervising the packers. And they want to know how productive they are, how quickly they do it. So there is algorithmic management, that's a new thing now.
So maybe that's what the future will be. Will be the robots doing the
algorithmic department,
the caregiver for your for the elderly.
It might be, but it's very difficult to find people. That's a problem.
Yes, please.
Is there usually a rule or a concept of like using certain data sets with priority over others, between like robotic data sets or like simulations versus human operated like recorded data, or is there?
So there is quite a lot of work about people demonstrating actions to the robots and robots learning from it. And this is the learning from demonstrations that I am talking about. They are learning from databases of games and things like that of people that are less expert or more expert. Our algorithm did better than this algorithm. Moving to robots, I'm still not familiar with. We are working on it, and we are trying to get others to be involved in such projects, because it's a difficult problem and many open questions.